Welcome to another episode of BHY Solutions. We're always diving into all sorts of intricate topics, but today we're tackling something that feels almost magical, that very first spark in engineering conceptual design.
It's true. It can feel like magic, right? And we have a great starting point for this deep dive, thanks to one of our listeners, The Learner. They sent us some excerpts from innovativeconceptualdesign.pdf.
Okay, so innovativeconceptualdesign.pdf. What's the gist?
Well, one thing that really stands out from this book, and it's based on years of teaching mechanical engineering students and research, by the way, is how conceptual design, while obviously super important, it often lacks that really clear step-by-step methodology you see for other parts of the engineering design process.
That's interesting. So we know it's important, but we don't always have a clear roadmap. So let's break this down. What exactly are we talking about when we say conceptual design?
Yeah, good point. The book defines it as, and I'm quoting here, the thought process of generating and implementing the fundamental ideas that characterize a product or system.
Okay, that makes sense. But I mean, isn't that what engineering design is all about in general? What makes the conceptual part so special?
The key here is that it's about making a genuine leap. It's about coming up with a totally new core technical concept, something that just didn't exist before. It's not just refining or improving an existing solution, it's a totally new approach.
Oh, I see it. Like not just a better mousetrap, but like a whole new way of catching mice.
Yeah,
Can you give me an example just to make it crystal clear?
absolutely. Let's think about something we all use, pens. We had fountain pens for ages, right? They use capillary action, the way liquid moves in narrow spaces, to get the ink onto the paper. But then boom, along comes the ballpoint pen. It uses a totally different principle, a tiny ball that rolls and transfers ink.
Hmm.
Both right, but the core concept, the way they achieve it, is radically different.
Okay, that's a great example. So conceptual design is about those aha moments, those fundamental shifts that change the game.
You got it. And because it's about this newness, creating something that hasn't been done before, it's often described as a discovery process rather than just, systematically finding a solution in a handbook.
Makes sense. It's like you're exploring uncharted territory. So where does this conceptual design phase fit within the entire process of designing and engineering a new product?
So if we zoom out and look at the big picture of the whole engineering design process, conceptual design is that second crucial stage. It comes right after the first step, which is need identification and analysis. You can't jump to a brilliant solution if you don't know what problem you're actually trying to solve.
Right. You need that solid foundation first.
Exactly. And the book highlights that the spark for those new ideas, those leaps, can come from two main directions. Either from something called technology identification, where you look at what technologies already exist and how they might be applied in new ways, or from those deep insights you gain during the need analysis phase.
Okay. And speaking of need analysis, the book really emphasizes something called parameter analysis as a powerful tool for conceptual design. What's that all about?
Parameter analysis, think of it like a systematic way to take those initial rough concepts and really develop them into something more concrete and viable. It helps you create conceptual designs that are much more well-defined right from the start.
Okay, but isn't the goal to come up with the solution the best one?
You'd think so.
Yeah.
But actually, one of the key points the book makes is that during this stage, you actually want to aim for at least three or even more distinct conceptual solutions.
Multiple solutions. Why so many?
It's all about maximizing the chances of innovation. By exploring multiple paths, you're much more likely to stumble upon something truly novel and effective. And then once you have these different concepts, you move on to concept selection, where you compare and evaluate them to see which one has the most potential to actually become a real product.
Okay, so multiple paths to potentially uncover hidden gems. Makes sense. Now, let's go back to that foundation you mentioned, the need identification and analysis. Why is this first step so crucial?
This book is very clear. Every single successful design process has to start with this. You need to really clarify and quantify the design task. It's about getting those deep insights into the problem that will pave the way for creating a truly innovative product.
Okay, so what are we doing in this phase? What are the goals?
The main goal is to identify the real underlying need. And it has to be in those broad, solution-independent terms. It's not about jumping to a specific product or feature. It's about understanding the fundamental need in a way that's completely free from any preconceived solutions.
That makes sense, but can you give me an example to illustrate the difference between a real need and maybe like a more superficial need?
Absolutely. Think about the evolution of the typewriter. You might say, oh, the need was for clear and legible documents. Sounds reasonable, right?
Yeah, sure.
But here's the thing. Early typewritten documents, they weren't really widely accepted at first. There was a cultural barrier. So you could say that wasn't really the true market need at that point.
Interesting. So the technology was there, but the societal context wasn't quite ready.
Exactly. The real need that really drove the adoption of the typewriter, the one that was there all along, was the need for high-speed transcription. Businesses needed to produce documents faster. But here's the catch. The early typewriter manufacturers, they kind of missed a key part of that need.
Oh, what did they miss?
They focused solely on the machine, the hardware. They didn't fully grasp that the need also included training, teaching people how to actually use these newfangled machines efficiently. It was a package deal. Without skilled typists, the high-speed transcription need wouldn't be met. And that's partly why adoption was initially slow.
So the need wasn't just for the product, but for the whole ecosystem around it. Fascinating.
Exactly. Things really took off when organizations like the YWCA started offering typing courses. Suddenly, there was a demand for trained typists, which in turn created a huge market for typewriters. Later on, the introduction of visible writing typewriters, where you could actually see what you were typing as you went, addressed another key need.
Right, the need for more immediate feedback, less back and forth with the paper. So the understanding of the need evolved, became more nuanced, and drove further innovation.
Absolutely. And this brings up a really important point for any business, really. If you define your core business too narrowly, just in terms of the specific products you make, you're setting yourself up for trouble.
You need to be adaptable, ready for the next big thing.
Exactly. Like a lot of typewriter manufacturers, they vanished when the technology shifted because they defined themselves as typewriter companies. But imagine if they'd thought of themselves as being in the document creation business.
They might have been better positioned to adapt to, say, the rise of computers and word processors.
Exactly.
Yeah.
That's why companies like Kodak, they were smart to reframe themselves as being in the imaging business rather than just the film business. It allowed them to move with the times, embrace digital photography and all that. The key takeaway, for designers especially, is that you have to start by identifying the fundamental benefit, the real need that the customer is seeking.
So how do you go about actually defining that real need in a practical, concrete way? The book mentions something called a black box approach. What is that?
Yeah, the black box. It's a great mental tool. You basically imagine the product as a black box, a system where you have inputs going in, think energy, materials, information, and then outputs coming out. The need statement should describe that transformation process or just focus on the specific outputs required.
Okay, so instead of saying design a better mousetrap, you might say design a system that effectively eliminates rodents.
Exactly. That opens up the possibilities, right?
Yeah.
You're not limiting yourself to just a trap anymore. By stating the need in these broader functional terms, you encourage more innovative thinking. The book gives the example of obtaining Martian rock samples. If you define the need as obtain Martian soil samples, it opens up a whole universe of potential approaches.
You could have robots, balloons, maybe even some way to analyze the soil remotely without bringing it back to Earth.
Exactly. But if you jump to a specific solution, like design a rover to collect samples, you're really boxing yourself in, limiting your creativity.
I see. So keep it broad and focus on the outcome, not the assumed method. Are there other examples where this approach has led to some pretty creative solutions?
Oh, tons. Think about ship canals. The first one that comes to mind is the Suez Canal. It's a sea-level canal, a straight shot connecting two bodies of water. Pretty
Yeah.
straightforward, right?
Yeah, makes sense.
But then you have the Panama Canal. It's not sea level. It uses locks to raise and lower ships to navigate different elevations.
So a completely different approach to achieve the same fundamental goal.
Exactly. Now, imagine if the need was defined even more broadly, like transport ships across a landmass in a cost and time-effective way.
Okay, so we're not even assuming it has to be a canal anymore.
Right. And with that mindset, you get things like the Canal on Wheels in Belgium. They actually use water-filled rail cars to move ships over land. It's pretty mind-blowing.
Wow. That is a great example of how broadening the definition of the need can lead to some truly outside-the-box thinking.
Absolutely. But remember, need analysis isn't just about defining that core need. It's also about understanding all the constraints that come into play.
Constraints, like limitations on what you can do.
Exactly. You'll have explicit constraints. Those are the ones clearly stated in the design brief or directly derived from it, like size limits, budget restrictions, material specifications, things like that.
Okay, so the rules you have to play by.
Right. But then you also have implicit constraints. These are the ones that you have to dig a little deeper to uncover. They often come from studying the entire life cycle of the product, from manufacturing to use to disposal.
So things you might not think about at first glance, but that could really trip you up later on.
Precisely. These could include things like the operating temperatures the product will experience, regulatory requirements you have to meet, the skills and capabilities of the people who will be using it, even ethical considerations around the materials you source. It's a whole web of factors.
That makes a lot of sense. Need analysis is really a discovery process in itself, uncovering those hidden constraints.
You got it. The book breaks down these needs and constraints into categories like performance, value, size, safety, and any special requirements that might be unique to the project. And what's really important is analyzing the trade-offs between these categories. They often conflict, and figuring out how to balance them is key.
Trade-offs like if you want increased performance, it might cost more, or if you make something smaller, it might be less durable.
Exactly. Identifying these potential conflicts early on and finding ways to navigate them is crucial to making sure the final product actually meets the real needs and constraints.
Okay, so we've laid this groundwork. We understand the need, the constraints, the whole context. How do we actually move into the conceptual design phase and start generating those innovative ideas?
This is where parameter analysis really takes center stage. The book lays out a clear methodology, an iterative cycle that consists of three key steps: parameter identification, creative synthesis, and evaluation. You can think of them as PI, CS, and E.
Okay, PICSE. Let's break those down one by one. What happens during parameter identification?
This is where you identify the core issues, the critical factors that are absolutely essential to solving the design problem. These are the parameters. So for a car, parameters might be speed, fuel efficiency, safety features, things like that. But parameter identification is about figuring out which specific parameters are the most important for your conceptual solution. It's about asking the right questions to uncover the fundamental challenges.
I see. So it's about figuring out what really matters at this stage.
Exactly. And then comes creative synthesis, which is, as the name suggests, where you get to be creative.
So this is where the brainstorming happens, right?
Yeah, you can think of it that way. You take those critical parameters you've identified and you start generating potential configurations. Basically, you're sketching out in your mind or on paper the basic architecture or system that could realize that concept.
Yeah.
Might be a rough sketch, a diagram, a flow chart, even just a description, but you're starting to give those abstract ideas a more tangible form.
Okay, and then after you've come up with some potential solutions, you move on to evaluation.
Exactly. This is where you put on your critical thinking cap and you assess those configurations, those potential solutions. You're looking for weaknesses, unintended consequences, any areas where it might not effectively address the key parameters you've identified.
So you're basically testing your ideas before you invest too much time in them.
Exactly. And what's really important is that this evaluation often leads you right back to parameter identification. You might discover new problems or realize you overlooked a crucial parameter. And the cycle begins again. It's not a linear process, it's a loop, a constant back and forth between understanding, creating, and refining.
Okay, so it's this iterative process of learning and improvement. Makes sense.
And there's this related concept that's often helpful in this early stage called technology identification. It's basically about actively exploring the world of available technologies and identifying those that might be relevant or applicable to your problem.
So before you even start brainstorming specific solutions, you're taking stock of what tools you might have at your disposal.
Yeah, exactly. Like, let's say you're designing a robot plow. Technology identification might involve looking into different navigation systems, like triangulation versus GPS. What are the pros and cons of each? How might they impact the design? It's about expanding your awareness of the possibilities.
Okay, so technology identification is like surveying the landscape before you start building.
That's a great analogy. And the book gives this really interesting example of how identifying the right parameters can lead to radical innovation. It uses the example of neutral buoyancy in submarine design.
Neutral buoyancy. That's where the submarine's weight is perfectly balanced by the water pressure, right?
Exactly. And traditionally, this has meant that the operating depth of a submarine is closely tied to its size and the strength of its hull. The bigger and stronger the hull, the deeper it can go without being crushed.
So size equals depth. It's a fundamental relationship.
Right. But what if you could break that relationship? What if you could decouple those parameters?
You could have smaller submarines that could dive much deeper.
Exactly. And that's what technology can enable. Things like hydrofoils, advanced propulsion systems, those can change the game. They allow you to achieve neutral buoyancy in new ways, opening up a whole new design space.
So identifying those key dependencies and finding ways to break them, that's where the really big breakthroughs happen. Now, I'm really curious to see how this parameter analysis actually plays out in real-world design challenges. The book has some fascinating case studies, right?
Oh, tons.
Mm.
They really bring these principles to life. Let's start with the clear ice manufacturing example.
Okay, clear ice. Everyone loves those fancy cocktails with the crystal clear ice cubes.
Exactly. But it's trickier than it looks. The initial kind of naive understanding is that cloudy ice comes from dissolved air in the water. So the obvious solution might seem like, let's just remove the air.
Sounds reasonable, right?
Well, it turns out that's really difficult and expensive to do effectively. So that leads to the first crucial parameter identification step. You have to dig deeper. Why does dissolved air cause cloudiness? What's the underlying physics?
So you need a more nuanced understanding of the problem.
Exactly. And through research, they realized that the primary ice crystals that form are actually clear. The cloudiness comes from the secondary ice that forms later at something called the eutectic point. It's like the point where all the remaining impurities in the water, including that concentrated dissolved air, are forced to freeze together. And that creates all the cloudiness.
Ah, so it's not just about the air itself, it's about preventing that secondary ice formation.
Exactly. So the critical parameter becomes prevent the liquid from reaching the eutectic point. And that becomes the guiding principle for the creative synthesis phase. Most commercial clear ice machines, they focus on carefully controlling the freezing process to avoid that secondary ice formation.
So that deeper understanding of the problem led to a whole new design approach. That's really cool. Do you have another example that really shows that back and forth, that iterative nature of parameter analysis?
Oh yeah, the magnetic drives example. This one's a classic. The initial need, the parameter identification, is to transmit torque across a barrier that has to be completely sealed. Maybe you're dealing with hazardous materials, or you need to maintain a specific pressure.
Okay, so you need a way to transmit power without any physical contact.
Exactly. The first creative synthesis might be to use magnets. You have a set of magnets on one shaft, another set on a separate shaft, and a barrier in between.
Seems simple enough.
Right. But then comes the evaluation, and they quickly discovered that if the barrier is made of metal, you get huge power losses and a lot of heat generation due to something called eddy currents.
Okay, so back to parameter identification. What's causing these eddy currents? How can we eliminate them?
Exactly. And one solution might be to replace the metal barrier with a non-conductive material, like ceramic. But then, new problem. Ceramics aren't great under tensile stress, the kind of pulling force you might have from a pressure difference across the barrier.
So every solution creates a new challenge. It's a constant dance.
Absolutely. And this is where that iterative process is so important. The designers had to go back, look at the fundamental causes of eddy currents. Consider things like the speed, the magnetic field strength, the properties of the barrier material. They went through multiple cycles of PI, CS, and E until finally, Nova Magnetics Limited came up with a brilliant solution.
What do they do?
They created a laminar construction. Imagine thin metal rings separated by insulating gaskets. This design minimized the eddy currents while still being able to handle the mechanical loads. It's like a detective story, you know? Each evaluation reveals a new clue, a new challenge, pushing them closer to the final, elegant solution.
And the book has even more examples, right? Like the HVAC airflow sensor.
Oh, yeah. They explored all sorts of initial technologies like hot wire anemometers and pitot tubes before settling on a pendulum-based design. But even then, the parameter analysis was extensive. They had to consider things like the sensitivity of the pendulum to airflow, how to measure the angle of the pendulum in a cost-effective way, and eventually they came up with this really sophisticated split double pendulum design.
It's amazing how they kept iterating, refining the concept based on those evaluations.
Exactly. And the cut-edge sensor, the one for flooring removal, is another great example. They started with a simple idea, measure reflected light. But then they realized that ambient light would interfere, the flooring material wasn't always uniform, the cut edge could be tilted.
So a seemingly simple problem turned out to be quite complex.
And that's where the PICSE cycle shines. They went back to the drawing board, identified those new parameters, and eventually developed a much more robust solution involving creating and sensing a shadow of the cut edge using a lens and a whole system of multiplex light sources and detectors.
So they basically invented a whole new way of seeing.
Pretty much. And then there's the case study on low-cost industrial indexing systems. They needed a flexible, inexpensive way to move things in a precise, controlled way.
So I think automation, robotics, manufacturing.
Exactly. And they came up with two completely different conceptual designs, one based on a pneumatic cylinder and another using a spring for energy storage. In both cases, the parameter analysis have focused on critical factors like energy efficiency and overall cost. It's about finding that sweet spot.
Right, balancing those competing priorities. And we can't forget the equal channel angular extrusion, the ECAE metalworking example.
Oh, yeah, that's a good one. That shows how parameter analysis can even be applied to designing a whole manufacturing process. The need was to deform metal, create high levels of strain, without changing the overall dimensions of the workpiece. That led to some really creative solutions involving split dies and even moving channel walls.
It's incredible how versatile this approach is.
And finally, you have the ball mover design contest, which is a great example to illustrate these principles in a fun, competitive setting.
Oh yeah, the one where they had to design a mechanism to launch a ball as far as possible.
Exactly. The need analysis was clear. Continuously accelerate the ball, maximize the distance, minimize the moving mass of the mechanism, and that led them to some interesting initial ideas, like a drawbridge-like arm or a puller rod. And then the detailed parameter analysis, all that iterative refinement, addressing things like how to stop the ball, how to prevent the puller rod from lagging behind. It all beautifully illustrates how this structured approach can lead to truly ingenious solutions.
Absolutely. These case studies are so valuable because they show how this isn't just some theoretical framework. It's a practical, powerful tool that can be applied to real-world problems, from everyday products to complex industrial
I
processes.
totally agree. And beyond the systematic methodology of parameter analysis, the book also highlights some key mental mechanisms that are really helpful for fostering creative breakthroughs during conceptual design.
Oh, so it's not just about following a rigid process. There's an art to it as well.
Absolutely. One of the most important is the idea of stepping back. Basically, it's about consciously forcing yourself to look at the problem from a completely different perspective. It's about challenging your assumptions, those ingrained ways of thinking that might be holding you back.
So if you're stuck, try looking at it from a totally different angle.
Exactly. Like, imagine you're designing a bitter can opener. You might get stuck in the mindset of improving existing designs, making the cutting mechanism sharper or whatever. But stepping back might lead you to ask, do we even need to cut the can? Could we peel it open, melt it, find a way to dissolve the metal? It's about breaking free from those mental constraints.
It's like hitting the reset button on your brain.
Exactly. Another powerful mechanism is analogical thinking. This is where you try to find parallels and draw inspiration from seemingly unrelated fields.
So looking for solutions in unexpected places.
Exactly. Like, the book mentions how airbags, which were originally designed for cars, are now being used to cushion the landing of spacecraft on Mars, or how the principles of fluid flow can be used to understand stress concentrations in solid materials. It's about seeing those unexpected connections.
It's about borrowing brilliance from other fields.
Precisely. And finally, there's the ability to creatively identify and integrate constituent elements, the basic building blocks of your design, in novel and unexpected ways. It's about seeing those pieces and how they can be combined to create something truly new and functional.
So it's not just about coming up with a great idea. It's about having that mental agility to see the potential in different components and how they can work together.
Exactly. So for our listener, the learner, and for everyone listening, it's clear that conceptual design isn't just about waiting for that magical flash of inspiration to strike. While those moments are great, it's the combination of a systematic, iterative process, like parameter analysis, coupled with these powerful mental mechanisms that really drives meaningful innovation.
It's about being deliberate, being curious, being open to new ideas, and not being afraid to challenge your own assumptions.
Absolutely. By deeply understanding the real need, breaking problems down into those key parameters, creatively exploring solutions, and rigorously evaluating those ideas, engineers can navigate this often challenging conceptual stage and create truly novel and impactful products.
We've seen how this works in everything from everyday items like those clear ice machines to complex industrial equipment. and even in the creative energy of student design competitions. It's a reminder that even those seemingly magical leaps in innovation often come from a lot of hard work, a lot of careful thought, and a deep commitment to solving problems in new and better ways.
We hope this deep dive has given you a better understanding of this crucial phase in the design process. And maybe next time you see a product, you'll think about all the thought that went into that initial spark, that moment when someone said, "What if?"
And for our listeners out there, what stood out to you as the most intriguing aspect of conceptual design? What kind of everyday product do you look at and just think, wow, someone really had to think outside the box to come up with that? We'd love to hear your thoughts and maybe even explore some of the thought questions from the book excerpts the learner shared with us. This is just the beginning of a fascinating journey into the world of how ideas become reality.